Section 10.3, we're going to look at comparing two means like we did in 10.2, but this time we're going to look at what we call paired data. So we have an example here where we had identical twins who were separated at birth and then adopted, and one twin was adopted by a high-income family and another twin was adopted by a low-income family. We gave those twins IQ tests as adults, and here are their results. Okay. So the high income family twins had a mean of 109.5 and the low income family twins had a mean of 103.667. Standard deviations are pretty close, but if we look at these graphs, like it doesn't look like there's a huge difference. Like, yeah, B is a little bit lower, but there's not a huge difference. But when we do our study this way, we're ignoring the fact that these are paired data because our subjects here were identical twins. So wouldn't it make more sense to compare the twins directly to each other? So rather than the average of all the high income families and all the low income families, we want to know for that specific pair of twins, since most everything about them should be similar, if not the same, other than the family they were raised at, how much of a difference is it between the two identical twins? Okay, and when we do that, we see that there's a mean difference of 5.8 points and a standard deviation of 3.9. Okay, so when we are deciding which procedure to use, it depends on how the data are produced. Okay, so if you remember back in chapter 4, we talked about matched pairs experiments, and there were two ways that we could do matched pairs. We could have people get both treatments. So if I wanted to see whether music helps somebody learn, I could have them do a task while they're listening to music and a task while they're in silence, and then I compare that person to themselves. All right, and then the other way is if we have, like in this example that we just talked about, we have identical twins or people that are similar, and we give each of them one of the treatments and then compare them to each other. Okay, when we have a matched pairs situation, we have paired data, which means we should use a paired T procedure. So we're going to do a single mean versus two means. All right. Very important. These two things sound very similar, but they are actually very different. A difference between means, that's what we did in the last section. We have two independent random samples, and we are comparing the mean from both of those two groups versus the mean difference, where we are comparing each person either directly to themselves or to someone who is very similar to them. And then we are finding the mean of all of those differences. So let's look at some examples. I want you to pause and read through the example, and then we're going to talk about which procedure we should use. All right, so this one should be a paired T procedure because we are having one diver use both kinds of fins and comparing the time to remove to they themselves rather than the average of everybody. Okay, same thing, pause and read. In this case, we would want two sample T procedures, what we did last section, because we have two independent random samples. All right. And one more, pause and read. Okay, this again would be two sample T procedures because when we do each time period, we are randomly selecting who gets which wetsuit. All right, so we can do confidence intervals and hypothesis testing. All right, all of these conditions should look very familiar to you. All right, random, 10% if we are sampling without replacement, meaning we're not doing an experiment. And then normal/large sample, we either have to know the population is normal, have a sample size more than 30, or draw a graph and discuss that graph and say that it doesn't have any strong skewness or outliers. Okay, when those conditions are met, here is our formula. again, on your formula sheet. So the mean, sample mean difference, when they do X diff, that's what that means, mean difference, plus or minus, we're doing T star, and then the standard deviation of the sample difference divided by our N, all right? And then when we do T star, our degrees of freedom is N minus 1. Okay, so we'll go through the example. Still the same thing. State, plan, do, conclude that we've been doing over and over and over again. Okay, so we have a 95% confidence interval for mean difference where mean difference equals, and then we define our parameter. Check our conditions. Random, it says it was a random sample. 10%, because we were taking random samples of identical twins. I think it's safe to say that 12 is less than 10% of pairs of identical twins raised in separate households. And then for our normal large sample, because our sample size is 12, we got to draw some sort of graph. They chose to draw a dot plot. I'm a big fan of the box plot just because your calculator would do it for you, makes it easy to copy down, just like we've done in previous chapters. All right, so that doesn't look super skewed or anything crazy. So we can use the formula or we can use a calculator. All right, and here are your calculator steps. A lot of times, because we have small samples here, you're given full-on data, like you have this whole chart here, rather than just the summary statistics. So what we can do is we can type that data into our calculator. We're just typing the differences though. So if you look at this chart, I don't need the 128 or the 120. I just need the 8. So we're just typing those differences. If they don't give you the differences in the problem, you could do the subtraction in the list in your calculator. You don't have to do it separately. So in list 1, you could type 128 minus 120, 104 minus 199, and it'll do it math for you right there. All right, so a lot of times that's easier. And then for your test or your interval, choose list instead of stats, which we usually do, where we type in the summary statistics. Okay. Again, you can use a formula, or if we're going to use a calculator, let's write down the summary statistics that it gives us, and then our interval. Okay, and then same conclusion that we've done for every single confidence interval. We can also do a significance or hypothesis test. Same 3 conditions as our confidence interval. All right, and then our standardized test statistic would be T. Okay, and this would be our formula for finding T. And then we can find the p-value by using t-CDF in the calculator. Or you can do a 1 sample T test in your calculator as well. Okay, so here's another example that we're going to use to do a significance test. You can pause and read through this. All right, and so we want to know, do we have convincing evidence that the caffeine withdrawal increases depression score? So state, plan, do, conclude. All right, our null is that the mean difference is 0. There is no effect from the caffeine, and then our alternative is that it's greater than 0 because we're testing whether or not it increases. Okay, define your parameter and then give your significance level, just like we've been doing. Okay, check conditions. Random condition, it told us that the treatments were randomly assigned. Because it's an experiment, we don't need to worry about 10%. And so the normal large sample, we need to draw a graph. Again, they drew a histogram. I would stick with the box plot. It's the easiest one. Okay, and here are your calculator steps. Again, if you have summary statistics, we can choose variable or stats, and we can type in the sample mean, the sample standard deviation, all of those things. Or if they give us data like in this chart, then choose list and actually put the differences in your list. So again, we would do like 5 minus 16, 5 minus 23, 4 minus 5. Put those in the list, and then you don't have to worry about calculating the sample mean and sample standard deviation. Okay. Here it is with the formula. If you figure out those sample summary statistics and then use your formula and t-CDF, or we can use the calculator, okay, and use the data from the list. When you do that, let's make sure we write down our sample statistics, our sample mean, our t, and our p-value, just like everything we've been doing, okay? And then conclusion, we're going to compare our p-value to alpha. Reject, which means we do have convincing evidence. And that is it for 10.3.